Welcome to Lecture 11A, entitled Triple Integrals. So this is the first lecture where we actually start to look at volumes, that is objects in 3D. And so I made a note right at the bottom that it's important that you learn how to sketch the regions, since this will assist you in determining the bounds on the integral. This is probably the most challenging material that you've seen so far, and it really depends to a large extent on your ability to visualize. So this material is covered in Reading Assignment 3. There is actually a chapter in the textbook that dealt with this, but some of the material was completely out of sync with these lectures. So I rewrote that chapter in the textbook and made some changes so that effectively we are dealing with something now that is relatively seamless. There will be no major questions regarding ordering of material. So the objectives of this lecture are to develop the tools for computing triple integrals in a Cartesian coordinate system with functions as integration limits on the inner and middle integral. We won't deal with constant terms because it's relatively straightforward. We'll just go directly to having functions as being bounds on the integral. So the concepts and visualization skills. Integration is a sum, so this will be the Riemann sum in 3D. We'll look at the relationship between integration limits and the surfaces bounding the 3D region. And then lastly, we'll look at changing of the order of integration and also some examples regarding how to compute an average of a quantity. As usual, the second slide basically is just a summary of the contents of this lecture, so I'll just move on. All right, so the first thing is to look at how we end up with a triple integral, which means we have to start with the Riemann sum. An example I've chosen here is to compute a mass. So for instance, if you look at the diagram here, you'll notice that we've taken this prism and tried to basically discretize it into a number of volumes, these little boxes which are stacked one on top of each other just to fit within the prism. And if you look at the information associated with this little rectangular box, we pick a center point of this particular box labeled with an index k, and so this would be a k subscript, y k subscript, z k subscript, with the stars to indicate that we're evaluating the value of the function at the center of this little box. The differential volume of this little box, delta v subscript k, where k refers to the individual volume element, will be just delta xk, delta yk, delta zk. Usually delta vk's are taken to be the same. So delta xk, delta yk, delta zk will be the same for each one of these elemental boxes. It doesn't have to be so, but generally it's the way we set the problem up. Also, just as a reminder that in computers, if you have to calculate an integral, right, then typically, for instance, instrumentation, then typically what's implemented is a Riemann sum. Right, so the question of accuracy then comes down to how many little rectangular boxes do you want to fit within the volume, in which case your accuracy improves. So the definition then in this case for the Riemann sum, if we're going to compute the total mass within this pyramidal structure, is to take the mass density evaluated at some given point in a given volume element times the volume element size, which is delta Vk. And so every volume element will have a different value of functional value. This is a mass density. Mass density in this case would be kilograms per cubic meter. This has units of meters. So this will have units of kilograms for each little volume element. If we sum the masses, we get the total mass that you see here. And so the limiting process is to let each volume element go to 0, which means the number of volume elements goes to infinity. And in the limit, this is defined as the triple integral of fx, yz, dz, dy, dx. Now you might say, why did I use this ordering? It's, as will be shown, it doesn't really matter. It's why we call it an iterated integral, in that we can use any different order we want, but the justification for doing so will be described shortly. So again, here are just the definitions of the different elements that we see here. This here represents delta mass. So this would be basically for each little volume element, right? This is basically the contribution of the mass to each volume element. All right, so now we can basically quote the theorem, 16.5 triple integrals. Let f be continuous over the region. That is a given. And the domain in this case would be that a is less than or equal to x less than or equal to b. G of x is less than or equal to y is less than or equal to h of x. And g of xy is less than or equal to z is less than or equal to h of xy, where g, h, capital G, and capital H are functions, continuous functions. And then if these conditions are satisfied, then f is integrable over domain D, and the triple integral is evaluated as an iterated integral. So this is the general form of the expression. Here we've chosen to integrate with respect to z first, followed by y, followed by x. But as we'll be showing shortly, there's no need to keep to this sort of regime. We can change the order if in fact is advantageous. All right, so the next thing I want to do is to sort of make it clear how we interpret this Leibniz formulation, that is the geometric interpretation. And so in math, sometimes we sort of do everything in short form, but it's inferred that something is there which happens to be missing. So for example, let's look here. This is the formulation. This basically says that this is an upper bound and this is a lower bound on the value of z. The fact that this is a function of x and y means it's a surface. The fact that it's a function of x and y means the surface. So this is upper surface, lower surface. The next one is g of x and h of x, and that refers to dy. The problem here, though, is that a volume is bounded by surfaces. And the way this is formulated, it would be 6 surfaces bounding a volume. So something's missing. I mean, y is a function of g of x, but z is not mentioned. That means z can be anything. And then the last integral is between x equals a and x equals b. But neither y or z are mentioned, which means that y and z can be anything. So I basically rewritten this expression in the form of this expression here. So what does it mean? It means we have an upper surface and a lower surface. This would be a curved plane. All right, this would be a curved plane extending to infinity in the minus and z direction, same as this. So it's boxed in on 2 sides here. It's boxed in on 2 sides here. And we only need 2 more sides to basically close the volume. So in this case, x equals a, but y and z can be anything, means that you've got a plane. This is just a plane located x equals a, extending to infinity minus infinity in both the y and z direction. And this is a plane at x equals b, similar explanation given here. So effectively, this represents the boxing in of the domain. But we write it in this form, in short form. So this is just a summary then of the different points we just discussed. What are the bounds of the integral? What do they look like? What are the bounds on the middle integral? What do they look like? What are the bounds on the outer integral? What do they look like? And we realize that there are 6 surfaces that bound the domain. Just a reminder that when you set up a problem, you've got to make sure that this function is smaller than this one, less than. Same here. This is the lower, this is the upper. This is the lower, this is the upper. All right, so just a simple computation of mass given simple boundaries. Well, simple boundaries is you're given a solid box bounded by the planes x equals 0, x equals 3, y equals 0, y equals 2, and z equals 0. Okay, so it's a box. And so this is basically the picture that you see here, represented by these conditions all mentioned here. The mass density of the box decreases linearly in the positive z direction and is given by this function. And this, given it's a mass density, its units will be kilograms per cubic meter in SI units. All right, so we want to compute the total mass. So we set up the triple integral. So this is basically the mass density, 2 minus z dv, over the domain. Given that we're dealing with simple bounds on the domain, right? That means, for instance, we can set up dz, dy, dx any which way we want, because these involve only constants. This is not the case when these involve functions. You've got to be much more careful. But in this case, any order will suffice. So if we're going to do dz first, then these are the limits on z. If we do dy second, then these are the limits on y. And we're doing dx last, so these are the limits on x. And so this is just a simple calculation. dz basically means you hold y and x constant. When you do the integral with respect to y, you hold x constant. And finally, the last thing you integrate is with respect to x here, and the final result in terms of units is 9 kilograms. So this is just an explanation of the region over x that we're integrating, the region over y we're integrating, and the region over z that we're integrating. All right, so let's look at integration bounds in a little bit more detail, starting with the integral and moving to the outer integral. So if we basically write the triple integral in a slightly different fashion, this basically would represent, for example, with respect to dz, between an upper surface and a lower surface. And then whatever's left over here would basically have to be a function of both x and y, which means that we're integrating over a region. So if we look at this picture here, this and this are the same. Notice that this color here, orange, represents this surface, and this color represents this surface. And note that this surface with respect to z is greater than this one, which has to be the case. All right, the next thing you do is to figure out, well, what is the region? The region is the projection of this onto the xy plane. So it's like looking at the shadow. So it becomes this basic contour that you see here. So in this case, basically, if you were looking at the integration over region, you have the upper bound on the innermost, the middle integral, and you have the lower bound here, g of x, h of x. For the outermost integral, the bounds are going to be the larger being b, that's x equals b, and x equals a. And that means you'd be integrating over this region. So you integrate over this region and this height to compute basically the total value of the integral. So if this were a mass density, then we'd be computing the total mass contained within this object here. So just into a little bit more detail, the region, this just shows you that when you do the integral over the region, then we have the upper limit on y, which is this. The lower limit or lower bound on y is this. So that's h of x, this is g of x. And then, so these are curved, these would be curved planes, because don't forget it comes out of the page. Z can be in the minus and positive infinity direction, same here. And then this would be the outermost integral, x equals a, but y and z can be anything. So these would be basically a plane again that comes out of the page and goes in both directions. Similarly here, this is a plane at x equals b. So this is a way to interpret the region and the integration taking place. All right, let's take a more complicated problem and let's illustrate the need for the change of order of integration. And so you start by basically considering an integral of this form. You've got this messy looking integrand that basically is formulated as a problem in which you're expected to integrate first with respect to x, then y, then z. And the region basically is to be defined as from 0 is less than equal to y is less than equal to z, and 0 is less than equal to z is less than equal to 4th root of pi. Okay, so when you look at something like this, the first thing you want to do is to figure out, how do you picture it? And so that's probably the most trickiest thing to do, and we need to spend a little time trying to understand it. So let's look at the picture on the left, which is the result of the actual process of putting the picture together. So here we have integral with respect to x, which means this is x equals z and x equals y. So the innermost integral would have this basically being the axis, the surface that you're interested in, and you pick the surface which has got the highest value of x, which turns out to be this surface here. That's the surface x equals z. The next basically would be x equals y, right? Well, if x equals y, it means basically z can be anything, right? That turns out to be the blue surface that you see here, but it extends to infinity in the z direction. We don't want to throw all these lines in here because you wouldn't be able to see the object, but imagine it extends out this way and this way. Similarly on this surface, this way or this way. Notice that this surface basically has a value that's larger than this, but that's why this is the upper bound and this is the lower bound. And at this point they intersect. Okay, that's a good point to know, because one of the bounds obviously on the remaining bounds has to pass through this line or intersect with this line somehow. So we move to the second part now, dy. All right, that means in this case y equals 0. Y equals 0 means the xz plane, just the back side of this pyramid. And y equals z. Y equals z basically would be this line that you see here. But x can be anything. So imagine this being an inclined plane that just is extruded in this direction and this direction. it turns out that plane just touches that line. Okay, just touches that intersection line. Can't see it here, but that's exactly what it would look like. Just touches the line. And lastly, we're looking at integration of z between 4th root of pi and 0, which means the top surface and the xy plane. And so I've labeled these, color-coded these according to the bounds. So these are the outer bounds, the green ones are the inner bounds, and these two here, which would represent this one, this here, and this here, that's these two, that would be the inner bounds. So that's the way you basically set up the construction. This is a more complicated case because we have this intersection point, or intersection line. All right, so the question would be, can you integrate it? Well, don't try it. I wouldn't even know how to start this one. However, if you reverse the role here, that is instead of dx dy, do dy dx, then we will be able to integrate that. Okay, so that's the reason why we're going to switch. Out of curiosity, the number of ways that we could actually move x, y, and z around would be m factorial, which is just m times m minus 1, da da da, until you get to 1. So in this case, basically, we have 3, m equals 3. So 3 factorial would be 3 times 2 times 1. So there's 6 possible ways of reorienting that. So we're just picking one of them, which turns out to be the easiest, which is switch these two around, dy followed by dx followed by dz. Okay, so that's what we're doing. This link, by the way, allows you to view the region for 2 different integration cases under consideration, and also to see the bounding surface, the inner, middle, and outer integral for the 2 different cases. That is integral with respect to dx, y, dz, and integration with respect to dy, dx, dz. Okay, so now let's look at basically the fact that we're going to swap. So this is now swapping things. The question is, how did we get these limits? All right, so now what we have to do is to basically realize that if we're going to choose y first, this will be the first inner integral. So we're looking at surfaces basically which are y as a function of x of z. All right, and so from the original picture that we have, it seems like this surface here would be the uppermost surface, and this back surface would be the lower, the bottom surface. So that would be the region. It would be the region would be the xz plane. So that's the triangle that you see here eventually that we're going to be looking at when we do the 2 outermost integrals. But for the innermost integral, it's in the direction of y, which means y equals x would be the first one, and the other one would be y equals 0. Right, so that's basically why you see here y equals 0, followed by y equals x for the upper surface. The region would be basically what you see that's left over, which is just this triangle here, and I'll show an interactive examples to what this represents. These are basically just lines that's shown on the xz axis, but actually if you extrude them, right, these are surfaces. So this is a surface that extends out in the y direction. This is a surface that extends out in the y and x direction. And this is basically and the xz plane. This will be an extrusion in this surface. So these lines that you see are actually just the intersection of the surfaces with respect to the xz plane. Okay, so that means that for the innermost integral, the region, okay, we're going to do x first. So if this is x, this is the higher value, and this is the lower value. And so we would have x equals z being the upper bound, and x equals 0 being the lower bound. And lastly, we would have z would be this being the upper bound and the xy plane being the lower bound, which is what you see here. So now if you do the integration, the first one with respect to y, you hold xz constant. The next integral, you hold z constant. And finally, integrate with respect to z, and you end up with the answer pi over 4. So you can see how an iterated integral makes it possible to solve the problem, whereas the integration we started with was next to impossible to solve. All right, so here's basically an interactive version that you can look at. You can toggle for individual surface or regions. So for instance here, the blue areas, these are the projective surfaces on the xz plane, which were used to perform the dy dx dz integration, and the projected surface for the dx dy dz integration, which was the yz plane. And I've just mentioned here the equations x equals z, x equals 0, y equals 0, z 4th root of pi, z equals y, z root 4th of pi, corresponding to the intersection lines that you get when you look at the xz plane and the YZ plane for the two different regions. All right, so the next thing would like to look at is how you define the average of a function. And so the definition of average of a function of three variables. Here's basically how it starts. If f is continuous on a region domain D of R cubed, then the average value of f over D is defined as, we just put a bar over it, 1 divided by the volume of the domain, integrating the function of interest over the volume of interest. The volume of D is just a triple integral of dv. Okay, so next is let's illustrate this. Example. The problem statement is to consider a rectangular block of thermally conducting material occupying a particular region. Again, we've picked a simple region involving constant bounds, just to illustrate the process. Due to the heat surface on the surface boundaries, the temperature in the block is given by this function. Okay, it's just a value that's been given. And the objective is to find the average temperature of the block. So the solution involves two steps. First, to compute the integral of temperature over volume, and the second step is to compute the volume, and the final step would be to compute the actual physical average. And so the two intermediate steps are the ones indicated in red. So we take basically this integral here. Here's the value. This is the function for t, integrate over the volume. Again, because the integration bounds are constants, the order of integration is not important. We've chosen dz, dy, dx first. And so you integrate this function with respect to z, right? And then holding yx constant, then you integrate with respect to y holding x constant, and finally you end up with a result of 2000 over pi. So this is just an integration now. For the volume, basically, we have to integrate just dv, but dv is dz, dy, dx over this respective bound. So z value is from 0 to 1, y value from 0 to 2, and x value from 0 to 2. If you perform this integration, you get 4. Lastly, you take the ratio of these two, and you get approximately 159.2. This is the value for the integral of t dv, and this 4 value is the value for the volume. And it's the final answer that you get. All right, so that concludes Lecture 11A. Thank you for listening.